I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. Give me an interesting variable from the GSS. We'll just go around. Start with Tim.
Law 1, a robbery.
Uh-huh. Wait, so the variable is LAW?
1.
1.
LAW1.
Okay, great.
And I guess that stands for a robbery.
Okay.
And the question was, did any of the following criminal or legal been secured to use since the current month? That was in 2003.
Uh-huh.
And it was like a robbery, mugging, or sticker.
So the question is, have you been a victim of...
Basically I've been a victim of robbery.
Interesting.
Since 2003.
Yeah, that's great. I didn't know that variable was in there either, so that's cool. Gender. No.
Mine was also Rorschach. I was asked if you're a woman, your health, if you personally were at risk of health complications due to a pregnancy, would be okay to abort, and then if you were a man, would you recommend that your wife get an abortion?
Okay.
And I was what surprised the most interesting part was 87% said yes, which
87% said yes. It would be okay.
If it affected the health.
Oh, okay.
Because if you watch anything on abortion, they make it seem like it's a lot closer to debate.
Yeah.
Almost 90% of people.
That's a good point. That's very good.
I did passport and said, how proud of you of America? How are you of America usually following its achievement in sports?
How proud are we?
I seem pretty proud. There's a yes, no, I can't remember.
Yeah. Well, that's cool. I mean, you guys obviously got beyond the background demographic stuff. Part of the exercise is to let you know what data is in there. You know, you can say, okay, I'd like to do a paper on people's attitudes on abortions and how that maybe differs by race, differs by religion, differs by age. Tim's example is a great one where it says, have you been a victim of a violent crime? So there's that question. The person might answer yes, that they've been a victim of a violent crime. What other questions in the survey could a yes answer be associated with? Does that make sense, my question? What I think is interesting is you have a powerful question like that, or at least a situation where, wow, if you've been a victim of a violent crime, that's going to shape your perception of maybe the criminal system or a death penalty. And so you could see, wow, are people who've been a victim of a violent crime more likely to be pro-death penalty? You know, is there an association there? Whereas, the people who haven't been a victim of a violent crime are less likely to be pro-death penalty. So that's the direction that we're moving in, and that's actually the focus of today, is I'm collecting data, experiments, and observations. In that is this idea of association, or the association between two variables. And so it says two variables are associated if the values of one variable tend to be related to the value of the other variable. And so with Tim's example, the variable of law 1, is that associated with the variable death penalty? That's the thing that we're going to be looking at and seeing what the implications of that type of association is. So if we look at our Duke student survey, all the variables along the top row, what potential associations do you actually notice from the data? Just by looking at this data, what associations do you see? What two variables seem to be associated with each other? Okay. What is it that you sort of see? A trend that you see? Okay. As the value for height increases, the value for weight also seems to increase. Yeah, Chris?
I don't know if it's missed it. It said like almost like piercings and exercise.
Huh.
For some reason, a lot of them go like the less piercings, the higher the exercise.
Interesting.
Well, not everyone though.
Yeah. That's really good. And actually, any association rarely, I mean, almost never will it be locked in. If it is, then you know something's wrong with the data. Sort of like if you ask someone what their income is in dollars and then have another variable, what's your income in cents, those will be locked in. You know, say my income is $1, it'll also be 100 cents and, you know, straight through. But with most variables, it's not going to be like clear cut, but you'll see patterns. And so that's really good that you see like, I wonder, right now I'm just showing you the first 15 respondents, but if I showed you all 600, there's ways to test to see, is there a real association going on there more than just randomly being patterned together? The one that I saw was gender and piercings. Look at all these zeros are all men. So not terribly surprising, but again, it's another association that we see. But it doesn't mean that actually from this there's no woman who doesn't have a piercing. That's kind of interesting. If one person has 7, yep. Interesting. And do they exercise? No, not very much. So
One has 8 piercings.
an 8 piercing,
But
yeah.
exercise 10.
Wow. So the idea is when you're looking at variables, and especially within statistics, what we're interested in is the association between two variables. Then there's a unique type of association that is even more interesting to sociologists is this association a causal association? To kind of use some examples that you guys pulled up, when deciding about the potential causality between two variables, we need to identify or distinguish between the explanatory variable and the response variable. So the explanatory variable is the variable that's going to cause a certain outcome. It's going to explain why this sort of outcome occurred. And the response variable is the outcome, the thing that we're interested in. So with Chris's example, actually, how would you set it up? You were talking about piercings and exercise. So we see an association there. Mm-hmm. Now, it could just be two variables associated with each other, or there could be a causal relationship. And so if you were going to take a stab at a theory, which one would be...
I don't know, it's a tough one to kind of like work together because it's just piercings and exercise, I guess.
Take a stab.
I mean, I guess you can almost put in another variable too. It said also just like the more piercings were female. So I guess you could say that less females were exercising. It seemed like the males were exercising more
than females.
All 3 of those, because almost every piercing was female. And so more females that had less exercise, you could say.
Okay. You are way ahead of the game. So when we get about 5 slides up, you'll see that that's the perfect answer. Now that I disclosed the perfect answer.
I mean, one explanation would be if you exercise a lot and you're doing organized sports, it's harder to have piercings.
Okay.
So I would have more piercings because they take longer to heal. So
yep.
Because I don't have time.
Okay. So then in that scenario, which variable would be the explanatory variable? Is exercise causing fewer piercings? It's tricky. Well, so this is a good point. I mean, that's not even really a fair question because you could sort of argue it both ways. And so a lot of times when we're talking about causal relationships, it's like, well, wait, is A causing B or is B causing A? Or are they just associated but not really driving each other? So we're going to show a couple examples. It says being female is positively associated with getting body piercings. So what that means is if you're a woman, there'll be a higher likelihood of having body piercings. So then another way to look at it, does being a female cause body piercings? Let's say this was our theory. Which variable would be the explanatory variable? The variable that predicts an outcome that we're interested in. So female. The explanatory variable, the variable that's going to predict a certain outcome, is going to be, in this case, female. And then the response variable is the body piercings. That's the outcome of interest. Another one would be exercising is negatively associated with smoking. And by the way, this is how you make these statements of association. Because if you just said exercising is associated with smoking, you wouldn't know in which direction. You wouldn't know if it's exercising is related to more smoking or vice versa. So the negatively helps you know when one goes up, the other one goes down. So does exercising cause a person to not smoke? So what would be the explanatory? Exercising. So it's sort of like, as a person's level of exercising, does that cause a certain outcome of whether to smoke or not smoke? But you can also see this can be flipped around. Does smoking cause a person to exercise less? And again, it shows you that the causal relationship can really go in both directions, or it might be unrelated. It doesn't matter where the variables line up in the data set or anything like that. It's just more sort of our theory would drive these questions, and then we use statistics to test that. Height is positively associated with weight. Does being taller cause a person to weigh more? And if you look at any of these, they're not clear cut. You know, it's like, well, does being taller cause a person to weigh more? Well, I know some skinny tall people, and I know some fat short people. Is there a cause, or is it more two variables being associated, and there's another factor, sort of like what Chris is alluding to, that's sort of driving the overall relationship? So here's an example. If you look at global politics in developing countries, you have two variables. One is number of TVs that a country has per capita, and then the other variable is life expectancy. What they noticed when they gathered data on countries around the world on life expectancy and the number of TVs, what they found was a very, very strong relationship that as the number of TVs per people, per thousand, per capita increases, life expectancy also increases. So there's a huge initiative, not really, but to start sending TVs to all these developing countries to help increase the life expectancy, because they saw a very clear relationship that having TVs must improve life expectancy, because it's right there. We see it with all the data. What's the problem with this proposed way to benefit the world?
TVs aren't actually saving anyone's life. It's probably increasing for something else.
Okay.
If you have TVs, your GDP is probably higher because people can afford that much TV, they can afford healthcare.
Okay.
Themselves, vice versa. So I think it's just like they're not causal; they're just associated. With other factors.
Exactly. Yeah.
It could be like, I mean, it could just not maybe just the TVs. It could be just like the channels, like watching the news or something on the health tips and stuff. Could be a reason like people do it that way, not just the TV. But
yeah.
Be the channels on the TV.
Okay, so that's a good point. It could be interesting. Like, do these people have greater access to information that people in other countries don't have? And so that could be more closely related to having a TV. Or it could be, as Brittany was saying, like overall GDP leads to having more TVs and having greater life expectancy. So this is sort of a caricatured example, but you'd be amazed at how often researchers find a relationship and then say, oh, okay, X is causing Y. And they move forward with a huge agenda. But the main point in this is that association, just because there's association, doesn't mean that it's a causal relationship. So back in, I think it was the 1920s or so, they were doing research on causes of polio. And they basically, these researchers at universities had basically found out that eating ice cream was causing polio. And so here's a clip of how this research and this finding came about.
Freaking out. Well, hi there, boys and girls. This is Captain Kangaroo. Say, I'd like you to meet a friend of mine. So, you know, it's lots and lots of fun to have a pet to run, play, and jump with, isn't it? But did you know that there are some boys and girls who can't run and jump and play? So all because of a thing called polio.
When I think of bad historical assumptions about correlation and causality, I think of polio 100 years ago, when it was this horrible mystery that it was, claiming a lot of lives, and it was really scary because it mostly struck children. And there was a strong line of research that suggested that ice cream caused polio, that ice cream consumption caused polio.
Here comes Mr. Salty with soft ice cream now. The finishing and processing you get from Mr. Salty.
The reason that correlation was thought to be causal was that polio spiked in the summertime for reasons that really weren't very well understood, but it did. And ice cream sales spiked during the summertime. So these researchers had seen that whenever there was a lot of ice cream being sold and consumed, there was a lot more polio. And so there was really literally the beginnings of this kind of ice cream persecution to try to stomp out polio. And it sounds ridiculous, but you see it all the time now, people trying to fight against or build up something that they're sure is connected to something else, which it turns out just isn't.
So that's an example of 100 years ago, but even today, it still happens. And even you'll sort of fall into this trap as well, where you'll be like, oh my gosh, look what this is related to this, like this is driving this, and even your mind kind of wants to convince you that this is true, when in reality, it actually might not be a causal relationship. And so it's one of I'll say the biggest mistakes or errors in sociological research and statistical analysis is that people see a relationship and automatically think one is causing the other. But as Chris alluded to, the way to say, well, if it isn't causal, how is the relationship there? Like, how can they be associated but not causing each other? And it comes up to the point of confounding variable. And so it's a third variable that's associated with both the explanatory and the response variable. And that's what's known as a confounding variable. Let's see, Chris, your example was body piercing is associated with less exercise. And then you said, oh, there might be a third variable that sort of is associated with both of them. And what was that again?
It was the female.
The male, okay, so gender.
Yeah.
So in Chris's example, well, we didn't really clarify what the explanatory or response variable was, but the confounding variable would be gender. Let's just say we were thinking that piercing was causing less exercise. So piercing would be the explanatory variable, and the response variable would be exercise. What we're interested in is what's the confounding variable that really affects the outcome variable. And so that's where its gender seems to be really explaining exercise. So what you have is confounding variable, it's associated with both the explanatory and the response. So gender influences body piercings, and it also influences exercise. And so what it does is it brings into question this causal relationship. The relationship is still there, but it just says, it's not body piercings that's causing the less exercise, it's some other confounding variable, or a combination of other confounding variables, or even, as Brittany was saying, that body piercing might be causing some less exercising because of the things that you explained. But just to sort of look at these two variables and say this is causing that is a broad overstatement, and it's not taking into account all these other confounding variables. Yeah.
So you could explain it, change the or in the response.
Explanatory.
Explanatory in the response. You can, if you explain it well, you can flip them if you think it's the other way, or is it sometimes will always be one or the other?
Well, this is where theory comes in. So, and we'll be talking about this later on, is that you have a hypothesis. Just like Brittany was saying, okay, well, before you do any research, you have a theory, and you're like, I think body piercing leads to less exercise because of the health impairments and even just the general, it's harder to exercise if you have a lot of body piercings or whatever. And so that's your theory out there, and you basically want to go to the athletic department ultimately and say all athletes should be banned from body piercing because it's hurting our performance as athletes. And so that's your theory, and the athletic department director is going to say, well, do you have any evidence for this? And so you go and gather your data on all Duke students and look at the relationship between body piercing and exercise, and so then you would test to see if it's causing it. She's going to test if body piercing is causing less exercising and see if that's the case. But say you had a theory of people who exercise less don't care about their bodies and they're going to, pierce them all over the place. And so then you're going to develop a theory for that, go out and gather data and test for that. And it's hard to know, actually. I mean, both your studies won't necessarily be conclusive, but you'll be adding evidence, and then you might say, well, let's do an experiment, or let's do some other type of thing to further test our theory. The thing is, you start with a theory versus if you look at the data and you're like, oh, look at this data, I bet you body piercing causes this. You're sort of letting the data create your theory. That's not the direction that you would go in doing that. A lot of times people will say X is causing Y, and then someone will say, well, no, my theory suggests that Y is causing X. But then the really smart people will say, what about all these compounding variables that you haven't ever accounted for that are really driving this relationship? So it says whenever compounding variables are present or may be present, a causal association actually cannot be determined. You cannot say that a relationship is causal if there's confounding variables present. And actually, in reality, there's always confounding variables present. So with eating ice cream, that's the explanatory variable. Getting polio is the response variable. And let's see, do you guys remember what the confounding variable, what one of the hypothesized confounding variables is? Yeah. So hot weather, the confounding variable that influenced both ice cream consumption and getting polio. But there's also a ton of other confounding variables that could be influencing eating ice cream and getting polio. And so theoretically, you'd have to do a study that accounts for all the possible confounding variables, which is impossible to do. The other example is number of TVs per capita and life expectancy. So again, we're saying that number of TVs explains life expectancy, the outcome life expectancy. But what was the confounding variable that Brittany proposed? Remember GDP, wealth. Basically, as wealth goes up, both the number of TVs that are in the country goes up and the life expectancy goes up. And it brings into question, well, yeah, maybe TVs isn't causing an increase in expectancy, maybe it's wealth. So this all relates to how we collect our data. So we have the population, we grab a sample that's reflective of the population, and then we gather data on this sample. Now there's two ways to collect data, and these are pretty much the two typologies for how you would do a research project. And one is through an experiment, and the other is through an observational study. And so I'm going to unpack these a little bit, but there's two ways that data can be collected. So you have the experiment versus observational study. In the experiment, now this is sort of the key thing, is that the researcher controls the value of the explanatory variable. And maybe in medical terms, the researcher controls who gets the treatment. And so an experiment is a controlled environment. If you think about putting people into a lab or whatever, this picture of running an experiment on people, this is what's going on, is that the researcher is controlling who gets the value of the variable that they get. So, I mean, in extreme cases, the researcher would control who gets body piercings or not. You're actually controlling the explanatory variable. Whereas in an observational study, the researcher does not control the value of any variable, but simply observes the values as they naturally exist. And so a lot of survey research is observational study. So like the Duke student database that I have is just making observations. Like I think they probably asked how many body piercings do you have, but the idea was you're just observing. You could either ask the person or you could write it down. You're not manipulating anything, you're just sort of taking in data. Observational studies cannot be used to establish causation. And the main reason, or the reason, is that there's always confounding variables that have not been measured or accounted for in observational studies. That X is causing Y, you have to sort of eliminate or account for all possible confounding variables. Like Chris brought up one, but there could be a bunch of other confounding variables that are really driving this that don't have to do with body piercing. This is a limitation of observational studies, is that you can only sort of identify associations, but you can't claim causality. Again, go into this in more detail, but that's a key thing. You can't make causal claims when you're using survey data. However, confounding variables can be avoided through experiments by randomly assigning the values of the explanatory variable. So this is the difference between why you would run an experiment and why you would just do observational studies. The experiments allow you to eliminate confounding variables. I'll go in and explain how that actually works. So we start with a randomized experiment. That's sort of like what you're doing when you set up an experiment. And so in a randomized experiment, the explanatory variable for each unit is determined randomly before the response variable is measured. Yeah, the best example is to think of medical research. There's a new drug out, and let's say there's cancer patients or whatever, and this drug is supposed to cure cancer, remove cancer from their body. What you could do is say, and let's just use a simple example, saying like exercise is going to eliminate the cancer. In an observational study, you would go to all these people who had cancer and you would ask them, how much do you exercise? And then see the relationship between exercising and getting rid of cancer. But what you don't know is, well, did these people do a bunch of other things that helped or hindered their ability to lose cancer? In a randomized experiment, the explanatory variable is exercise, and you randomly determine who's going to exercise before the response variable is measured, before the variable of have you gotten rid of cancer has been measured. And so the ordering is very important in this. The explanatory variable is also known as the treatment, and in this case it has a value of either 0 or 1. And so did you get the treatment or not? And so that would distinguish between the two groups. So then the way you do this is you randomly divide the sample into two groups and assign one of the groups to receive the treatment. So you have your sample from the population, you say, okay, we're going to run an experiment, half of you are going to get the treatment, the other half aren't. And so what this does is that this assures that the explanatory variable, or the treatment, for each unit is determined by random chance alone and is not influenced by any other confounding variables. In my mind, this is kind of tricky. Like, I was like, wait, how does that work? Because there's still confounding variables in there, but the confounding variables have been randomly distributed throughout your sample at this point, so they're no longer going to have a direct effect on the outcome.
So when you're saying like randomly, could it mean like it could be like the placebo, like someone's taking one group's taking one pill, one's taking the placebo? Is that kind of like
random? Because I think this, for me at least, this is confusing as I'm thinking about it conceptually, because I'm like, well, how do you eliminate confounding variables? Because there's always factors that could be causing that could be associated or influencing the outcome that we're interested in. Another key factor in these randomized experiments is to have a control group, like Chris talked about. So when determining whether a treatment is effective, it's important to have a comparison group, which is known as the control group. Because if you just had people exercise, but you didn't have a control group of people not exercising, you wouldn't know if it was having a significant effect, or just in general people overcame cancer as a whole, as a population. You need a control group that wasn't getting the treatment to see if it was effective. So in all randomized experiments, you need either a control group or two different treatment groups. You could say, is exercise more effective in treating cancer than radiation? You could compare two groups. If we were going to set up a randomized experiment, this is how we would do it. You'd start by gathering a random sample from the population. So it always starts with getting a sample. Let's say there's 100 people in the sample. Then you need to randomly assign the value of the explanatory variable. You can do that by putting all the names into a hat and randomly pull out the names to go into different treatment groups. And this is a key thing. It needs to be randomly assigned. You can't say, okay, all the women go over here, you're going to get the treatment, and all the men go over here, because you've just taken a potentially confounding variable and sorted by that confounding variable. It has to just be randomly assigned. And so one way of doing it is put all the names in a hat. Another way to do it, like if I wanted to randomly assign the 6 of you to an experiment, I could put your name on a card, each of your names on a card, shuffle the deck, and then just randomly distribute the cards into two piles. The idea is to get the groups to be randomly selected. So you have a random sample, and then you randomly put them into two groups. Or you can use technology, which is often what's done, is the random number generator. So it takes your random sample and then randomly distributes them into the 2 treatment groups. Yeah?
Would it ever go back and like make sure they're truly random? I don't know, because I just remember like if you flip a coin, like it'll always end up being 50-50. You get like 10 tails in a row. Like if you randomly shuffled cards, there's still a chance that all the boys would end up wanting all the boys. Or like,
and I've thought about that too. I thought, because I had that exact same question. I was like, well, but what if by chance? The key for that is if your sample is large enough, it won't happen. So yeah, if you think of this scenario, it could be, just because we have 6 people, the chances of it sort of being non-random are much higher. And that's where sample size is important, and that's why you need a certain amount to make sure it's randomly. So that's a good question. Okay, so we're going to do a real-life experiment with it so the concept can hopefully sink in. There's a study on we want to do a study on caffeine and academic performance. And so the research question is, does consuming caffeine before an exam undermine your performance on the exam? This thing right here, n equals 100, what does that mean?
Yeah, he shows big and little. That's sample.
Sample, awesome, perfect. So basically, we're going to be working with a sample of 100 people. We've randomly selected 100 students, and that's our sample. So in this research question, what is the explanatory variable? What variable is going to lead to a certain outcome? Chelsea? Consuming caffeine, yes. So the explanatory variable, the thing that we're interested in, is the effects of caffeine on the outcome, which is your performance on the exam. The variable would be, did you consume caffeine before the exam? Okay, and so then the response variable would be exam performance, exactly, your grade. If we were going to do an observational study to test this research question, here's how it would be. We would simply gather data from the 100 participants. We'd have our sample of 100, and they would take the exam. First question on the exam would be, did you consume caffeine before taking this exam? And they would just answer yes or no. And then we'd also, after they took the exam, we'd have their exam grade. And so we might find an association between caffeine consumption before the exam and exam performance. But what would be a limitation of doing it as an observational study? Chelsea?
If you don't control how many hours of sleep they got or how much they studied before the exam.
Exactly. So there's other confounding variables. So it might be all the people who consumed caffeine before the exam had been up all night studying and were crashing, or they could have been up all night partying too. There's all these other confounding variables that could be sort of feeding into this association that we found. And so that's a limitation of an observational study. We can say that, if we find this to be true, we can say that caffeine consumption is associated with exam performance, but we can't say that it causes poor or better exam performance because of these other confounding variables. But if we find a relationship, we can't make a causal claim that caffeine consumption undermines exam performance because of confounding variables. And you guys name some of the confounding variables. You guys are on top of it. We could control for all these factors. So as Chelsea said, we could say, how many hours of sleep did you get before, at the top of the exam, we could add more questions, like how many hours of sleep did you get before the exam? What did you do the night of the exam? And try and what's your gender, and also what's your math SAT score, and all these other confounding variables. But the list is endless, and it's just impossible to account for all those things. So we could never, with observational studies, we could never make a causal claim. So that goes on to why we would do a randomized experiment if we want to make a causal claim. So the explanatory variable is consumed caffeine before the exam. The response variable is your grade on the exam. So in a randomized experiment, the way you set it up is we randomly assign the value of the explanatory variable for each participant. Any ideas of how we could do this? We have a sample of 100 students. Yes?
Only randomly put them into 2 groups.
Perfect. To do this, we'd randomly select 50 students. And again, it's important that they be randomly selected. It's not like, hey, are there 50 students who want to drink caffeine? Because, again, you would get the ones who are like dead tired and they're like, please give me caffeine. So you need to randomly select them and then have them consume caffeine before taking the exam. And then you would forbid the other 50 from consuming caffeine. Because if you just said do whatever you want to the other 50, some of them might consume caffeine or not, and so you need to control for caffeine consumption. So you require 50 to take it and require 50 not to take it. I won't do this to you guys. I have another experiment. The key of this is that it assures that the explanatory variable for each person is determined by random chance alone and is not influenced by confounding variables. Let's see, I don't know if it was Brittany or Chris who said, well, how do you know it's going to be randomly assigned? But the idea is when you do split the group up in 50, and it's a large enough group of 50, you're going to have some people in this group who takes the caffeine who spent all night studying, and you're going to have some who spent all night partying, and you're going to have in this group some who spent all night, whatever the variable, and you're going to have some women in this group and some women in this group. And so what it does is any variable or any factor that would have affected exam performance has been split up into the two groups. And so it evens itself out. And the only factor that hasn't been split up into the two groups evenly is whether or not you're taking caffeine. And so we've isolated that one variable into the two groups, whereas all the other confounding variables have been randomly distributed across the two groups. Do you guys believe that, buy that? Yeah, you can basically think of any factor. You're like, oh, but what about there's some of those people in this group and some of those people in this group, so they would even each other out, whether it's getting a better grade or worse grade. So if we run this experiment, we put 50 people in one group and have them take caffeine, and another 50 not take caffeine, they take the exam, we get the exam grades, and look, we find a relationship that all the people who took caffeine before the exam, on average, did better than the people who didn't have caffeine. Can we make the causal claim that caffeine consumption actually undermines exam performance? Let's say that the caffeine people did consistently worse on the exam. Can we make the causal claim? Would there be other things that we need to account for? So we can make it? Can we sort of, if we ran this experiment, can we make a claim? We see the relationship that caffeine consumption is associated with poor exam performance. Can we make a causal claim? Yes. Rachel, McKay? I mean, is it as simple as that, or is there other things that we would need to do?
Some people need to be smarter than others, right?
Control certain things.
Okay, control certain things. So explain that.
Because some people could drink as much caffeine as they like, because maybe they're already smart. I mean, it might not even affect anything.
Uh-huh.
And some people might not touch caffeine, and they've never done well in that class.
Yeah.
Because if it's a certain class or something, because you can't have like separate classes because if you're taking you have to take the exact same exam.
Yep. Yep.
So I mean, some people could be struggling in that class already. Some
Mm-hmm.
people are already doing well, so it's hard to
yeah.
that too.
Now, those people, so you have the group that takes caffeine, and then the group that doesn't take caffeine. Which group would those people more likely be in?
Like the ones who are doing worse? Or
Yeah.
I guess it could, I mean, I feel like it could be the caffeine side.
Well, but we randomly assign them.
Yeah, so you'll never know. I mean, like, you never know who.
So, and there's 100 students in our sample, and we took 50 and we put them in here, 50 in here. And let's say there's 10 students in the class and they're just not good at statistics. And so regardless if they take caffeine or don't take caffeine, they're going to bomb the test, right? So those 10 people, which group would they likely end up in? Where would they be?
I mean, if they're randomly assigned, you'll never know. I mean, you could have like 8 in one side.
Yeah.
Is there a way I don't know if there's a way you can know. Can you look at like people's grades before you get the turn, or does that not make it random anymore?
Yeah, no. So if you have a large enough group, you might need to do more than 100. But let's say you did 1,000. If they're randomly assigned and there's only 10, they're going to be fairly evenly distributed, even enough to sort of make a wash. So the low-performing people are going to pull down this average grade of this group, and they're also going to pull down the average grade of this group. And that's where I think you're bringing up a good point, because intuitively you're like, but what if, all these what ifs, and that's where the random assignment is key, because what that does is it eliminates all these other things, which are completely legitimate and valid things. It's like, well, what about this, or what about this type of person? Or you might even say, but caffeine has different effects on different people. But then what that might actually show is that there's no relationship. It doesn't mean that caffeine is going to have an association, because we might run the experiment and find that there's no correlation whatsoever.
So caffeine could make it worse, but it's already low.
Yeah, But now, is there still a distribution of grades? So even if the grades range between a 40 and a 60, there's still a range of grades, right?
Okay.
It isn't like everyone gets a 40.
Okay. Oh, so you're doing, okay, I got it.
And we're taking the average grade. It's a great question because it is, to me at least, it's intuitively, it's like, I don't want to buy it. I'm like, but how can you eliminate all confounding variables? And the key of it is the randomly assigning and having a large enough sample size. Because if we only did the 6 people in this class, there's a good chance that one side would be weighted in a particular direction that would be throwing off the experiment. And we will be talking about what sample size we would need for this. But that's a good question, and it isn't intuitively obvious. But if you, in a sense, do the math, you actually ran your own experiment. You sort of had 100 people, and you marked 10 of them with an X as like the low-performing people, and then we shuffled the cards and distributed them into 2 groups. I bet you this group would have 4, and this group would have 6. And the next time we did it, this group would have 5 and 5. Next time it would be 7 and 3. And on, if we did that 1,000 times, it would come out to be about 5 in this group and about 5. That's a good point, though. Look it, you even brought up my question. What about the multitude of confounding variables that could affect exam performance? And it's because people have been randomly assigned to be in the caffeine group and the no caffeine group, the values of the confounding variables will be evenly distributed between the 2 groups. So it's even if there's just 10 who are poor performers, or if there's 90 who are poor performers, they're going to get evenly distributed, or whatever factor you're concerned about. Because the explanatory variable is randomly assigned, it's not associated with any other variables, and thus confounding variables are eliminated. And so you have all these confounding variables, but when you do a randomized experiment, you sort of eliminate its ties to any other confounding variable, whether it's I don't do good in math, or I'm a male, or whatever. And so then that opens up the door to make the causal claim that caffeine consumption influences exam performance. So then we go on to what you talked about, placebo and blinding. The control groups should be given a placebo, a fake treatment that resembles the active treatment. The reason for this would be using a placebo is only helpful if participants don't know whether they're getting the placebo or the active treatment. So if we ran the experiment and I gave everyone a nice cup of Starbucks, the caffeine group, they would know, I'm getting caffeine. And the other group would know, I'm getting nothing. And so that would affect it. Whereas if I just had a caffeine pill and I gave it to the 50 in this group, and I had a pill of nothing or whatever, non-active ingredient, and they took that, neither group would know whether they were getting the real treatment or just a fake treatment. And so that enhances your experiment. It eliminates some of the psychological factors. See, like, that would be a confounding variable because the people in the no caffeine group, all of them would have a skewed psychological effect. Like, I'm not getting the treatment. And so actually, this group that you just randomly created, you sort of imposed a non-random effect on that group. So that's where you want to keep it as random as possible so there's no confounding variables. If possible, randomized experiments should be double-blind. Neither the participants or the researchers involved should know which treatment the participants are actually getting. And so, in a sense, I shouldn't even know. If I was running the experiment, I shouldn't be like, okay, I know I'm giving these people the caffeine pill, so I'm going to watch them. Or it's just better if I don't know. I just sort of say, here's a bag of 50 pills. I don't know if they have caffeine in them or if they're the placebo. That's the idea of a double blind. Like, you don't know and the researcher doesn't know. Because even I could skew it by treating you a different way. So this is kind of an interesting thing that comes up in experiments. It says often people will experience the effect they think they should be experiencing even if they aren't actually receiving the treatment. Just by me giving you a pill, this no caffeine group, they're like, ooh, I'm getting like some energy boost or something. I must be getting something this good. Or especially if it's like a red pill, or I don't know. So you had this psychological effect that, getting a pill has a positive effect or is going to affect my outcome. This is kind of interesting. This is one study estimated that 75% of the effectiveness of antidepressant medication is due to the placebo effect. Yeah.
Do you not tell them what kind of pill they're taking, like to experience like a caffeine, you don't feel junky.
Yes, exactly. No, and so when it's ethically possible, you can do that. Sometimes you need to let people know we're doing a caffeine exam performance study. Will you be willing to participate? If it's ethical, then yeah, that's the ideal. But even getting a pill, just by virtue of getting a pill, has the effect, even if you don't know how it's going to affect you. Here's an interesting clip that talks about placebos, and this is all in the context of experiments and getting treatments.
Now, you've all heard of the placebo effect before, when something with no known therapeutic value can actually make people feel better. It's a great trick our minds play on us, that by believing and expecting something to work, it actually does. But what's weird is that the strength of the effect can differ for some really strange reasons. For example, the same placebo can treat pain half as well as aspirin, while at the same time treating pain half as well as morphine. Morphine's a much more powerful painkiller, but a placebo is half as effective as both. Saying a placebo will reduce pain reduces pain, but saying that the same placebo will increase pain increases pain. Believing that a placebo will make you feel better will make you feel better. Believing that it won't has the opposite effect. Now, placebos aren't just pills. They can be creams, injections, surgeries, or drinks. You can even get placebo buttons. They don't actually do anything, but they sure as hell make you feel like you're in control. But not all placebos are equal. The effect of the placebo is bigger when the pill itself is bigger, or if you have 2 instead of 1, or 2 once a day instead of 1 twice a day. And a capsule will usually be the pill, and a syringe will usually be the capsule, and anything with a big ass science machine can outperform any of them. A plain pill works worse than a branded one. A discounted pill works worse than a pricey one, and even a pill in a plain box does worse than one that's all shiny and shit. Placebos that are blue work best as downers, and placebos that are red are better as uppers. Studies have shown that people who take their meds on a regular basis are less likely to die than those that don't, even if those meds are all placebos. You can even get addicted to placebos. In one study, a group of women took placebos for more than 5 years. 40% of them suffered withdrawals afterwards. In fact, the effect of placebos can be so strong that some people want them banned from sports. But I mean, how would you even test for that? Placebos don't even seem to work from place to place. For example, in Germany, using a placebo to treat ulcers works better than anywhere else in Europe. But using a placebo that treats hypertension doesn't work nearly as well as it does for its neighbours. Now, remember that all of this is about comparing things that both have nothing medically effective in them, which goes to show that a placebo isn't about what's in it, but about the beliefs that we load onto it. Our minds create the medicine, and that is pretty freaking weird.
So the point about this, one is that it's just really amazing that something that has no therapeutic effect or value can actually have all these effects. What it's showing for our purposes is that when you run an experiment, it's good to give both groups the same thing. So any type of placebo effect that might be out there is introduced to each group equally. It's not to say that, oh, we shouldn't use placebo. It's more to say if you don't use a placebo, the group that is getting the treatment that actually has to take a pill is going to experience a placebo effect from that. And so psychologically, they're going to be like, oh, I'm getting a pill because it's going to make me less depressed or whatever. And so by giving it to both groups, you can, and again, the people who placebos are going to affect, who have that psychological disposition, are going to be randomly assigned to the two groups. So the idea is if you don't introduce a placebo, the people who actually get the real treatment, because we're running an experiment. We don't know if caffeine really affects exam performance. It's not a foregone conclusion. It could be just the placebo effect. If we find a relationship and we only give these people a pill and we find this strong relationship, it might just be the placebo. It's like, oh, the professor gave me a pill before the exam, and so I'm going to do better. So you eliminate that by giving both groups a pill. Any questions about placebo or how that works? What Chris alluded to, when ethically acceptable, it's even better if the participants don't even know the nature of the treatment they're receiving. You know, it doesn't help to say we're giving you caffeine because we think it will undermine your exam performance. That would kind of freak you out or whatever. And so you're like, well, caffeine, I get really jittery, I'm going to get really nervous, and all this stuff. So when you can do it, it's best that they don't even know. They just sort of know you're taking a pill. Some limitations with randomized experiments, because they are ideal in the sense of making causal claims, but sometimes they're not ethical. Case in point, if I ran the caffeine experiment on you guys, you'd be like, hey, I don't want you messing with my grade any more than you're already going to, so I don't want to be a part of this. And so I couldn't require you to be a part of my experiment. And so I need volunteers, and you might not volunteer for that. It might not be economically feasible. I mean, to truly run a good controlled experiment on a large sample of people can get really expensive. It's not always the case. I'll use Tim's example of Law 1. Have you been a victim of a violent crime? We could run an experiment on that, but that wouldn't necessarily be, it is possible, but it might not be ethical. So there's a lot of things that we'd love to run experiments on, but there's limitations into what we can actually run an experiment on. And so often we have to do the best we can with the data from observational studies. You might not be able to make a causal claim, but I think, again, with Tim's example, with related to being a victim of a violent crime and your feelings on death penalty, if we find a really, really strong relationship, that's meaningful in and of itself. That it shows that there's a strong relationship. Now, you don't know if people who are pro-death penalty are more likely to be victims of violent crime. Maybe you live in a neighborhood that has higher crime rates, and so then you're naturally inclined to be pro-death penalty. The causal relationship could go the other way, but basically it's still okay and important to find strong relationships. It doesn't mean that these observational studies have no value. It's just we can't make a causal claim. And then randomization, okay, this is sort of an overview of the last two lectures. So there's two levels of randomization, and randomization is sort of the key to getting good data. The question is, was the sample randomly selected? If yes, then you can generalize to the population. Remember yesterday or 2 days ago we talked about if you aren't randomly selecting the population, you might have a skewed group that you're studying. If that's the case, you can't generalize from the population. And then the second element of randomization is, was the explanatory variable randomly assigned? If yes, like in the case of an experiment, then you can make causal claims. And if no, you can't make causal claims. This is kind of key, and this will sort of come up again throughout the course, is the explanatory variable randomly assigned? Is it an experiment going on? Or was it just an observational study where, whoever showed up to the class having drinking caffeine before the exam, that's who we got. Say we did the observational study of the caffeine test, you could still find a relationship. If at the beginning of the exam we had everyone write at the top, did you consume caffeine before the exam, and we gathered all the data, we might find a relationship. And we might find a very strong relationship. There's implications for that, but we can't ultimately say that caffeine causes poor exam performance. But we can say we have a lot of evidence that there's a strong relationship between consuming caffeine and performing poorly on the exam. A nuanced difference, and so you don't want to say caffeine causes poor exam performance, but you can say there's a very strong relationship. Okay, I'll just walk you through this so you can put it in your mind, but you can go back and read it. It's like taking a random sample and conducting a randomized experiment is the ideal, but it's not always achievable. In fact, it's rarely achievable to do both a random sample and a randomized experiment. Because think about, if you're running an experiment, you won't get a random sample of people who want to participate. So it's sometimes hard to get both. And so if the focus of the study is to use a sample to estimate a statistic for the entire population, all you need is a random sample. So like if I want to know how many Duke students take summer session courses, I don't need an experiment for that, because I just want to know a statistic. I want to know what proportion take summer session. If the focus of the study is to establish causality from one variable to another, you need a randomized experiment, and you can settle for a non-random sample. There's sort of a trade-off. If you want a statistic about the entire population, definitely need a random sample. If you want to establish causality, you definitely need a randomized experiment. So not just an experiment, but one in which the people are randomly split into two groups. Basically, the assignment is problems in the book. And as you're going through the assignment, if you have any questions, shoot me an email, and then I'll send the answer out to the rest of the group. So some of you have already done that. and that's been helpful. So what we're going to do for part 2, and what I'm thinking, I think the best thing would be type it up so that you have a copy of it and then print it out and give it to me, because you're going to be reusing this information. It's going to be building towards your final project, and no sense in having to write it all out and then wait for me to hand it back. Type up part 2. Part 1, I think, is probably easier. I mean, you can type it if you want, but mainly for part 2. So what we're going to do, the 10 variables that you looked up 2 days ago or yesterday, you're going to find 5 different variables that you think may be associated with one of the 10 variables that you selected. So, Tim, you could say, okay, one of the variables I selected was law 1. I need to find one variable that's associated with law 1, or that I think would be associated. You don't even have to find it to be associated. And then explain why you think those 2 variables would be associated. You can't use death penalty because I already gave you that example. But basically that would be the thing. It's like, find a variable in the GSS that you think would be associated with law 1 and just identify, here's the variable I think would be associated with law 1, and here's the question that it asks, and here's why I think those 2 variables might be associated with each other. And then do that 5 times. Pick 5 different variables from the 10 and find one that's associated with it.